If we have finished rocks and minerals, we've had the test 1 and test 2, and we talked about the 3 types of rocks: sedimentary, igneous, and metamorphic rocks. And when we were talking about sedimentary rocks, we made mention of weathering, because we talked about the fact that the rocks had to be broken up into small sediments, and that was weathering. And then those sediments had to be moved from one spot to another, and that was erosion. And so now we're going to talk about weathering and erosion, and we're going to talk about what weathering is, the 2 types of weathering: mechanical or physical, and chemical weathering. And then we're going to also give examples of each of those types and talk a little bit about erosion. Now, weathering by definition is the physical and chemical processes that break down rocks on the surface. And there are 2 different types of weathering. One is chemical weathering, and the other one is physical. And sometimes you might hear me use the term mechanical weathering. All right, now, if it is physical weathering, all that means is that we're going to take whatever those rocks are, and we're going to break them up into smaller pieces. See these small pieces right here? Those small pieces are still the same rock. All that's happened is that we've changed the size and the shape of it. On the other hand, if it's chemical weathering, materials are altered or dissolved. Now, you see this is a picture on the left of a graveyard, and I'm sure that all of you have probably passed or have even walked in a graveyard. And you've noticed that there are sometimes the tombstones, some of them you can read the writing quite clearly, others you cannot. Some of those that are made up of marble are the ones that easily weather and you can't really read them. But the ones that are made up of granite, you can read the dates and the names clearly, because granite is not affected as much by chemical weathering as would limestone and marble. All right, now mechanical weathering, all that means is that the rocks are going to be broken up into smaller pieces, but each small piece is going to still be the same rock. If we can think of it in another light, let's say that we had a sheet of paper and we tore it into 50 pieces. Each little piece will still be the paper. The only thing we've done is change the size and the shape of it, but it's exactly the same paper. All right, and so when we break rocks into smaller pieces, we increase the surface area, and when that happens, that causes chemical weathering to take place easily. And to give you an example of what that kind of looks like when we increase the surface area, now on our left we have this big cube, and if we decide to cut it up into smaller pieces, we would expose more surface area. So that would be more of that cube that would be exposed to weathering. And look here, we have even smaller ones. Think of this big thing as a white potato. And we did not have a microwave, but we certainly wanted it to cook in a hurry. So we would cut it into smaller pieces, and the smaller pieces that we have, the more surface area we are exposed, and therefore it will cook faster. Now, the physical weathering process begins with the formation of natural cracks, or we can call those joints that are in the rocks. And we're going to talk about some of those physical processes that are involved in mechanical weathering. And if you look at this, this says it's frost wedging. Well, we can see these cracks or joints here. This that you see is an example of water. And so if water gets into the cracks and it freezes, it expands. We know that water will expand when it freezes, because if you've ever put a soda in the freezer and forget about it, and you notice that when you go back and it's frozen, what happens to it? So frost wedging, all that happens with that is that the water will seep into the cracks or the joints. When it freezes, it's going to make that crack or joint larger, and that's going to help to break it up. Salt crystal growth. All right, now in a dry climate, or sometimes along the seashore, we can have salty water that seeps into the pores or the openings within the rocks. And when the water evaporates and the salt crystals precipitate in the pores, they're called salt wedging, because as the crystals grow, they're going to push those grains apart. Still, that's mechanical or physical weathering. And then this is sheeting or exfoliation. Well, let's look at this word. Ex means outside. Remember, we talked about extrusive igneous rocks, and we've talked about foliation because foliated texture is one of the textures of metamorphic rocks, where we see the bands or the layers. And you can see with this exfoliation, sometimes it's referred to as onion skin peeling, because we get these thin little layers, but those layers that are there are still the same rock. So all that we've changed again is the size and the shape. Now, in granite, exfoliation joints will split the rocks into what we call onion skin-like sheets. And that's why we sometimes refer to exfoliation as sheeting. And then we can have biological activity. Now, if you look at this, we can have plants that grow in the cracks or the joints of the rocks. And when they grow, as the roots get larger, that will make the crack in which the plant is growing larger, so that will break it apart. But even though plants can cause root pry to occur, plants also have a lot to do with chemical weathering, and we're going to see that. So the roots grow within the cracks. That's the part that's root pry, and they eventually cause the rocks to split. So we've done root pry, salt crystal growth, exfoliation, and we've done frost wedging as examples of physical or mechanical weathering. Now, you've seen mosses or lichens, and lichens are a combination of fungus and algae. And as these things, as well as plants themselves, grow on the rock, they produce weak acids. And when they produce weak acids, that's introducing a new chemical, and therefore that's going to be chemical weathering will cause chemical weathering to occur. So plant roots can cause root pry, which would be an example of mechanical weathering. But at the same time, they're producing weak acids that promote decomposition, or it's going to break down the minerals chemically, and therefore they're going to produce chemical weathering too. Now, any of the processes that is going to change or alter the internal structure of the mineral by removing or adding other elements, that's going to be chemical weathering. And the most important agent of chemical weathering is water. And then we know that oxygen dissolved in water will oxidize iron-rich minerals. And when we use the term oxidize, that should remind us of oxidation. And oxidation, we know, can produce rust or iron oxide. And this is an example. If you look right here, you can see the reddish brown color. So whatever this rock is, it had minerals in it that were rich in iron, and therefore we were able to see that. So oxidation has occurred. And see, the mineral that contains, it's going to contain iron, and it will react with atmospheric oxygen in the atmosphere, oxygen dissolved in the water, and therefore it's going to cause them to rust. All right, now you've heard of carbonic acid, and that's the weak acid that's formed when carbon dioxide dissolves in water. When carbon dioxide dissolves in water naturally two ways. When it rains, we know that the atmosphere has in it carbon dioxide, and as the rain falls, it will dissolve some of the carbon dioxide in the atmosphere, and that will produce carbonic acid. And also when organisms die and decay, they also release carbon dioxide. And when the water percolates through the soil over this, carbonic acid is also produced. So two things that are required for the production of carbonic acid would be carbon dioxide, and then we need to have water. And here's an equation. Now, I know some of you are looking at this and you see something on here that is not correct. And we'll talk about it in a minute. All right, carbon dioxide plus water, that's going to yield carbonic acid. Two ways it's formed. Remember from the previous slide? When it rains, the carbon dioxide in the atmosphere dissolved in it, and we get carbonic acid. Or when organisms when organisms decay and the water percolates over them in the soil, we're going to get carbonic acid. Now, this should be a lowercase a because this is calcium carbonate. Remember, calcium carbonate was the name for the mineral calcite. And we also learned that calcite happens to be the mineral that makes up limestone. Limestone, the sedimentary rock, when it undergoes metamorphosis, can become marble, but it's still calcium carbonate with C lowercase a, CO3. And when it combines with carbonic acid, and that's the weathering that we're going to have, and it's going to produce calcium bicarbonate. But the key thing that I want you to know from this is the balanced equation for carbonic acid. And I'm sure that in your chemistry classes or in physical science, you had to balance equations. And all that simply means is that we have to make sure that we have the same number of each kind of atom on both sides of the arrow. This side, these are the reactants. This would be the products, okay? Now here are some agents of chemical weathering. Carbonation, we have acid rain, hydrolysis, oxidation, plant acids. Now we just talked about plant acids. Remember, as plants grow, or as we can have lichens that are organisms, and we can also have mosses that grow on the rocks. They produce weak acids. And we talked about oxidation, which occurs in rocks that have minerals that have a lot of iron in them, and it's going to react with the oxygen in the atmosphere or the oxygen dissolved in water. And then we'll talk about these others. When we talk about carbonation, that's also a type of chemical weathering. And it talks about the fact that when rain goes through the air and into the ground, it dissolves carbon dioxide, and that's going to produce the carbonic acid. And that acid will react with the calcite in the rocks when it seeps into the cracks. And that's going to cause chemical weathering to take place. Hydrolysis was one of those terms on there. Hydro is the prefix that means water. So you know it has something to do with water. So hydrolysis is the chemical breakdown of a substance when combined with water. And didn't we just say earlier that the most important agent of chemical weathering is water? All right, now here's a common example of hydrolysis, and that's in the feldspar that's in granite. Because when granite is exposed to hydrolysis, it is the feldspar in it that changes to clay. So if we start off with feldspar and we end up with clay, that means that chemical weathering has taken place. And so then we can have physical action, because this is the sand, which has a whole lot of quartz in it. Now, in your textbook, you're going to have a complicated equation on page 102 that's going to talk about how granite weathers. But the key things, when you look at that on page 102 in your textbook, key things you need to keep in mind are some things that we've learned before. That granite is felsic. And if it is felsic, the first part of this reminds us of the most common silicate mineral, feldspar. And we also learned that feldspar loves to hang around with quartz. So if granite is felsic, it is composed of quartz and feldspar. And when it is exposed to carbonic acid, that's the acid that we talked about that is formed when carbon dioxide is dissolved in water. These are the three products that we're going to get. One of them would be clay minerals. We just talked about the fact that the feldspar that's in there is going to be weathered chemically, so you're going to get clay minerals. And then you'd get silica and soluble salt. And the soluble salt happens to be potassium bicarbonate. But if you were asked that question, what are the three products you get? It's okay if you say clay minerals, silica, and soluble salt. You don't have to know the name, the particular name of the soluble salt, okay? So when you look at page 102, please do not think that you have to memorize that complicated formula that you see on that page. Now, obviously, weathering is not going to take place at the same rate for everything. All right, so we're going to talk about factors that affect the rate of weathering. One of those factors would be the mechanical weathering. Mechanical weathering is going to break up the rock into smaller pieces. The smaller pieces that we have is going to expose more surface area. And so that would make it much easier for chemical weathering to take place. All right, rock characteristics would be another. The type of rock it is would have a lot to do with if it's going to weather easily. For example, in a warm, moist climate, if you have limestone and marble, they're going to be easily weathered because all it takes is that rain and then the carbon dioxide in the atmosphere to do that. So the characteristic, or we could say the composition of the rocks, and also we can include the size of the rocks in that. And then climate would have a lot to do with that because we would not expect weathering to take place at the same rate if it was a dry climate as opposed to one that is warm and moist. Now you should remember this as somebody's reaction series. And I'm sure that you've thought now that it has something to do with Bourne's reaction series. All right, now every one of these minerals from olivine to pyroxene that we've called augite, amphibole that we've called hornblende, and biotite, which is a type of mica, and then whether it's sodium or calcium or sodium feldspar, whether it's potassium feldspar, we recognize every one of these names as the names of silicate minerals. What is it that all these minerals have in common? They all have as their building blocks the silicon oxygen tetrahedron. Now, if you look at this, you can see that the minerals that are the first ones to crystallize out, they're here, and they crystallize out at high temperatures. And so if these minerals are the ones that crystallize out at high temperatures, if they are on the surface of the earth, they're going to weather faster because they're going to be least resistant if they are on the surface. All right, now let's use an analogy that's not about minerals. Let's say that we all went to the supermarket and we came back with a gallon of ice cream. Let's say that half of us put the ice cream in the freezer. The other class decided that we were just going to leave it on the desk and wait until an hour and decide that we were going to eat it. Well, those of us who decided to put the ice cream on our desk put our ice cream in an environment that was least favorable for it, and therefore it's going to melt in a hurry. But those of us who decided that we were going to put our ice cream in the freezer, we had it in a stable environment for it, and so it wasn't going to melt as much. So getting back to the minerals, if olivine crystallizes at high temperatures, that's far below the surface of the earth. If those minerals are in rocks that are on the surface of the earth, they're going to be the least resistant to weather, so they'll weather easily. You may have forgotten, but if you look back at Bourne's reaction series, you're going to see that the rocks over here that have these minerals would be basalt, as an example. And then as we get down here, the rock that would have potassium feldspar, muscovite, mica, and quartz would be granite. So with that in mind, on the surface of the earth, if you have an outcrop of basalt and an outcrop of granite, you would expect the basalt to weather easier. And the reason for that is because the minerals that make it up were those minerals that crystallize out at high temperatures below the surface of the earth. And on the surface of the earth, that will put them in the least resistant environment. So marble, which is made of calcite, weathers easily in the presence of carbonic acid. But the silicates, I'm talking about the feldspars, the quartz, olivine, and the micas, they're going to weather in the same sequence as they crystallize. So what does that mean? Look at it again. Olivine crystallizes out first. Pyroxene, and here we go. These are at high temperatures on the surface of the earth. That's the least resistant environment. They'll be least resistant. And so they're going to weather easier. They're the first ones to crystallize out on the surface of the earth. They'd be the first ones to weather. Okay, so that makes this statement, silicates weather in the same sequence as their crystallization, makes sense. Now for the climate, remember we said that the rate of weathering is affected by the climate? Well, temperature and moisture are important factors. Warm temperatures and high moisture are important for chemical weathering to take place. We also know that human activity can influence the composition of the atmosphere, and therefore that can affect chemical weathering. If we keep increasing the amount of fossil fuels, and the fossil fuels are going to, some of them will give off sulfur gases, and these can combine with water vapor, and they can produce sulfuric acid. And so human activities will affect the composition of the atmosphere, and therefore they will affect chemical weathering. Now, if we break the rocks into smaller pieces, that's the sediments. Have you ever ridden in the mountains and you see the sign that says watch for falling rocks? Well, high up on the mountain top, some weathering is going to take place, whether it is frost wedging or exfoliation or any of those other types of weathering that we talked about. If we get those smaller bits of sediments, those sediments sometimes fall off the mountains. And when they do, we say that that's erosion, because how erosion differs from weathering is that the sediments are removed or transported or they're carried away. So they're moved from the top of the mountain or wherever they are to another place. That's erosion. That's done by water. That's done by wind. Glaciers can do that, and also gravity can do that. So if we have the weathering that takes place on the top of the mountain, and if we get those sediments to move from the top of the mountain to the foot of the mountain, gravity did that. And sometimes they're eroded away by water, wind, and glaciers. Now here's an example of something that you probably know, and this is that we can refer to it as the hydrologic, or we commonly refer to it as the water cycle. And when you look at the water cycle, you can see that there are processes that take place. Processes that will get the water into the atmosphere, that will cause the clouds to form. And also the process that will return it back to Earth, and what will happen to it once the water gets to the Earth. All right? And for water to get into the atmosphere, evaporation has to take place. And evaporation, by definition, is we're going to have the liquid to change to a vapor. All right? And that's normally, we would expect for most of the evaporation to occur from over the water. You see another term here, that's transpiration. That's the fancy word that we use for the water that enters the atmosphere that's lost from plants. So now we get the water into the atmosphere. Eventually, the water vapor is going to cool off. And when it does, we're going to get clouds to form. And how do we get those clouds to form? By a process that we call condensation. Condensation means that we're going to change from a vapor or gas to a liquid. And how that is going to occur is there are some things within the atmosphere that are going to serve as centers around which the water vapor can collect. And these things could be things like smoke particles, dust particles. And so we call these things condensation nuclei. And that's two big words for centers around which water vapor will condense. That's what we call them, condensation nuclei. So that gives us the clouds. So we have the water into the atmosphere. We have the clouds formed by condensation. But if we want the cycle to continue, we have to have precipitation. And precipitation happens to refer to how moisture returns back to the earth. It could be in the form of rain, snow, sleet, hail, whatever. Okay? Now, when the precipitation occurs, there are some things that we can figure out looking at this diagram that happen to some of the precipitation. Some of it we will have infiltration, seep into the soil. Okay? Sometimes we will have runoff to occur. Just this week, it rained a whole lot in our area. And so they had flood warnings to occur so we can have runoff. But if we want the cycle to continue, some of that water also needs to evaporate. So three things that can happen to the precipitation. We can say infiltration, or it seeps into the soil. We can have some runoff and then evaporation to occur. Now, here's what we've done in this video. We've talked about weathering. We've defined it. We've divided into two types, mechanical or physical, and then chemical weathering. We talked about agents of mechanical weathering. We also talked about we also talked about chemical weathering, and we defined terms like carbonation, hydrolysis, oxidation, and then we gave examples of these, and then we ended up with the hydrologic cycle. The next time I come back to you, we will talk about soils, and we will learn ways to classify soils and some other things that we need to know about soils. So have a good evening and expect another lecture soon.